Not summer still.
Sorry, do you hear me, Lucia?
Yeah.
Thank you. Okay, so we will start with the next talk by Lucia Cordova. She's originally from Guanajuato, and then.
No, from Aguascalientes.
Where are you from, Lucia?
Aguascalientes. But I studied in Guanajuato.
Correction. Then I read that you graduated from Perimeter, did a master and PhD at Perimeter, and now you are postdoc at École Normale Supérieure in Paris. And Lucia will talk, as you can see, from conformal correlators to analytic S-matrices CFP1-QFP2.
Okay, thank you. Thanks for the introduction and for the invitation. It's great to be back in this virtual conference. So today I'm going to talk about this paper, which came out recently with Ife He and Miguel Pablos. So it's the first iteration of the talk. Have patience. The main idea of this project is to extract non-perturbative information of S-matrices from certain limits of conformal correlators. So this limit is the flat space limit, which I will introduce next. And why would we want to get information of S-matrices out of conformal correlator? So one motivation is that there is a very nice and rich interplay between the S-matrix and conformal bootstrap. Already in this paper here, we know that both of them are related via this rigid holography. So the idea is that if we start with some quantum field theory in an ADS background, in some D+1 dimensions, we know that this induces a conformal theory at the boundary, so in D dimensions instead of D+1. So if we want to recover some flat space physics, what we can do is to take the radius of ADS to infinity. That gives us flat space. And this limit in the conformal theory relates to having large dimensions. And this comes from the usual holographic dictionary, where you have certain masses for your particles and conformal dimensions on the other side. But crucially, there is this radius of ADS appearing here. So that by taking infinite radius, you need to take all dimensions to infinity. So this is the limit of the conformal theory that we will study, such that we recover some flat space physics in some D+1 theory. And by the way, we send all dimensions to infinity, but with some fixed ratios. So we keep the ratio of masses fixed, and we take the limit in this way. So this is one motivation, the interplay between S-matrix and conformal bootstrap. Another one is that we would like to understand better the analytic properties of scattering amplitudes. For many things, including this S-matrix bootstrap, one usually just assumes certain analytic properties, which are partially or not fully proved. And instead, for conformal theories, these conformal correlators are very well understood. So we can take advantage of that and try to get information from there that lets us know about the analytic properties of the amplitudes. So this is for the motivation. By the way, feel free to interrupt and ask questions. So to be more precise, what I'll be discussing here is a map between a 4-point function in a 1D CFT and a 2-to-2 scattering amplitude in 2 dimensions of identical particles. So here phi, and they have the same mass on this side. So the explicit functions I will be working with are these g of z. So it's a function of one variable, which is the cross ratio defined here as these differences between the points in which we evaluate the fields. And the amplitude that appears here, where the variable S is the center of mass energy, which is P1 plus P2 squared, so the incoming momentum. So the main idea that I want to discuss here in this talk is how do we start from a function that looks like this? So we know there are these branch points from the OPE. And how, by taking this flat space limit in which we send all dimensions to infinity, we recover some function which has also some cuts from the two particle thresholds, but can have many other non-analyticities, like poles for bound states, other types of poles for anomalous thresholds, etc. So this will be the goal of the talk. Okay, so to review a bit the setup, the starting point will be the position space map that this gentleman proposed. So that this map between correlator and S-matrix is actually very simple. For 1D to the kinematics, it's simply setting the cross ratio of the conformal field theory to the center of mass energy S with some normalization. So if you see here, we had some branch points at 0 and 1, and they become branch points at 0 and 4 and squared. So this is a very simple map. And they proposed this limit here, but this limit is actually only well-defined for some z in the complex plane, in some domain D. So what we will see here is that we will need to do some analytic continuation from the region where it's well-defined to the full complex plane. And this is why we write this flat space operator like this. So first we take the limit where it is well-defined, and then we analytic continue into all the complex plane. So to see an example of how this operation works, let us see the simplest case, which is that of generalized free fields. You can think of them as the CFT dual of free fields in ADS. Or if you just want to think about the correlator, it is given by just weak contractions. So this 4-point correlator has 3 weak contractions. So it gives just this is the final answer. But I will take advantage of this to remind you about the OP. So any CFT correlator can be expanded using the OP in this way. So you have some OP coefficients squared between the external particles phi phi and this operator with dimensional delta, in which we are summing over. And then you have the conformal blocks, which are purely kinematic factors. Sorry. Which are purely kinematic, and in this case, in one dimension, they're just these hypergeometric functions. So the dynamical content of the theory is in these OP coefficients, or structure constants, I think Matt was calling them. So for these generalized free fields, you know the correlator in this analytic way, but you can also expand it in conformal blocks, and you see that these OP coefficients are just these gamma functions. I wrote them because I will be using a free all the time, so just to say it once, it's something very simple. And the operators that go in the OP have dimensions 2 delta phi plus 2n. Okay, so that's the reminder of the OPE. But now let us see how this flat space limit works. So first, we can take the limit, just starting from this expression here. And you see clearly that you either get 1 or infinity. So whenever you're inside these unit disks, so see between 0 and 1, for instance, these two terms blow up, so you get infinity. However, if you're outside these disks, you get plus or minus 1. So the idea now is to analytically continue this plus or minus 1. And it's just a constant, so it's trivial, the analytic continuation here. And we define these flat space limits of the generalized free field correlator to be just 1, which is the free theory S matrix. So are there any questions at this point? Okay, so now the idea is, how do we do this operation for more general correlators? And for this, I will use 3 different elements. One is Polyakov blocks, another extremal functionals, and lastly, 2 different bounds, one on correlators and another one on OPE coefficients. So the first one is Polyakov blocks. As I was saying earlier, we can use the OPE to decompose the correlator in this way in terms of conformal blocks. But you can also decompose it in terms of some other blocks called Polyakov blocks, which have the crucial property that they are crossing manifest. So they satisfy this equation here. And there are different advantages for one or the other, but we will use this one here. For those of you who are familiar with these drawings, you can write these Polyakov blocks in terms of Witten exchange diagrams. So Witten diagrams are like Feynman diagrams, but in ADS. And you can also expand them in terms of conformal blocks for summing over certain dimensions. But we don't really need this. The other thing we will use about the Polyakov blocks is that they have a relation to a certain type of extremal functionals, which I'll review next, which we call master functionals. So we can write them in terms of some analytic functionals, omega. That's all we need about Polyakov blocks. Now let's go into the extremal functionals. This will be a bit more technical, but I think it's very useful, not also for the talk, but for many things in Bootstrap, specifically CFT Bootstrap. So let me review these nice functionals. So the idea in the conformal Bootstrap is to basically solve the crossing equation. And this crossing equation, you can write it in terms of this crossing vector, which is the difference of the conformal block evaluated at z and y minus z, using the OPE in this way. So it's just rewriting the crossing equation. But to extract really information from this equation, what you can do is to act with some linear functional, which is some functional that acts on this crossing vector and spits out some number. So a trivial example would be evaluating the crossing vector at a point. This is a particular choice of a functional. Here we will use something a bit more general, which is some contour integral with a kernel acting again on this crossing vector. So with different kernels, you get different functions. And by acting on this crossing equation with a functional, you get the sum rule, which you can use to constrain data, the CFT data, which are the spectrum, so the dimensions that you have in the theory, and the OPE coefficients. So to see how this can be done, let me remind you that these are the OP coefficients squared, these coefficients A. So in unitary theories, they are positive. So you have a sum of things with positive coefficients equal to 0. So to see how we could constrain this data, let us think of the following functional. So in a picture, let's say it looks like this. And the characteristic is that it is positive or non-negative for dimensions above a certain number, delta star. So it is positive from here all the way to infinity. And it can be negative in this region here. So then the sum rule, which is just the functional acting in the crossing equation, looks like this. So since these A's are positive, we have some terms which are negative and some terms which are positive, equal to 0. So if we have something negative plus positive, we can make things equal to 0, that's fine. But imagine we propose a theory such that its dimensions are only in this blue region. So then already with this equation, we know that this spectrum is not compatible with the crossing equation, and we can rule it out because sum of positive things cannot give 0. This is the usual way in which the numerical bootstrap, CFT bootstrap works. So you construct functionals that do this and you rule out space in the theory space, regions in the theory space. Okay, that's one possibility to constrain CFT data, but you can also just get bounds. So now imagine the following. You have just one operator in this negative region. Let's say it's the identity with dimension 0. And you want to bound the OP coefficient for an operator with dimension delta B. So since all other possible operators in the theory will be in this blue region, then you see that from here you can derive easily this bound. So from these extremal functionals, you can either rule out possible theories or possible spectra, or get bounds on different things. So different functionals naturally lead to different bounds. So yeah, are there any questions about this? I know it's a bit abstract. All right, so this is about the extremal functionals. Now, let me review 2 bounds we will need. So first, the one on OP coefficients below this 2 delta phi, which I'll call the threshold, because it's the 2 particle threshold in the amplitude. So in the large delta phi limit, there is the sine-Gordon functional, which was constructed in this paper here, which leads to a bound on the OP coefficient for an operator with dimension delta B. So what they found here is that this OP coefficient in the flat space limit is bounded by above by the coupling of the sine-Gordon breathers. So if you were here last year, you might remember this plot here. So it also comes in the S-matrix bootstrap for 2-dimensional theories. But here we just need that it is something finite. So that this OP coefficient A is bounded by something finite, except, okay, here, more on this later. So this is one bound we will use. And another bound is generated by these master functionals. So these functionals are designed such that they give bounds on the correlator at a given point. So they have some parameter, W, which will be the point at which we evaluate the correlator. And the bound they give is the following. So you have this subtracted correlator, that is bounded by above by the generalized free boson correlator and by below by the fermion one. And the subtracted correlator is simply the correlator itself minus the Polyakov block expansion below this threshold. So we'll see this bound is very useful. And as I mentioned earlier, these functionals here have a relation to Polyakov blocks, which we'll also use. And in general, they're hard to construct analytically for any delta phi, but for infinite delta phi, it's easier. And the kernel which defines this functional is just this. So it's some Cauchy type kernel. And in this paper here by Paulus, it was also shown that with these master functionals, you can arrive to a dispersion relation for this subtracted correlator. So as you see, this already looks like a dispersion relation for the S matrix, and we will use it. Okay, these are the tools. Now let me pass to the results section. So the main point of what we did is that we can extract the expected analytic properties that we have in all S matrices, like these cuts here, from the sum of Polyakov blocks above threshold. And then all the really the interesting part of the S matrices would arise from the Polyakov blocks below threshold. So from these flat space limits of this part of the sum, we will get the bound state poles, possible anomalous thresholds, etc. So we see that this flat space limit nicely separates below and above threshold, one which gives the non-analytic, the juicy part, and then another function which is analytic in the cut plane. And we know already, since this part above threshold is simply the subtracted correlator I mentioned above, before, which has this dispersion relation, that indeed we can write this function simply as some dispersion relation like this. And we actually saw already the flat space limit for the identity operator in the example one. Why? Because the Polyakov block for the identity operator is just the generalized free boson. And we saw already that the flat space limit of that is 1. So that's one block below threshold. But what happens for some other delta, which is not the identity, below threshold? So let us see how this flat space limit works for a single block below threshold. And what we see here is that the flat space limit gives rise to a bound state pole. And this is actually what we expect, but we can prove it. So I will explain in the next slide more details, but the limit of this Polyakov block will give a finite part, which is this bound state pole part. And then we have another term which can diverge or is 0 in this large delta phi limit. So in the complex W plane, we have some regions here outside these blue blobs where we have just this finite part. And inside it, this other term blows up, so that then the flat space limit, which requires this analytic continuation, we will get rid of these blobs and leave only the bound state poles here. So in pictures for a single Polyakov block, we see that the large delta phi limit becomes the bound state poles for the S matrix. So let us see in a bit more detail how this arises. Yeah, there are many formulas in this slide, but it's just details, so don't worry if you don't get all of them. One thing we need all the time is the large delta phi limit of the conformal blocks, which looks like this. Crucially, there is some part which is exponentiated to the delta phi. So just keep in mind this factor. There is Z, the variable in which we are evaluating here. And then this MB is related to the dimension itself with this relation here. It's just delta B is MB delta phi. And this expression here has a saddle point at large delta phi at a particular ZB, which is related to MB in this way. So we will use this later. Then another element is this bound on the OP coefficients I mentioned before. So these OP coefficients below threshold are bounded by above by this sign covariant coupling. And there is also this A free sitting around. And this A free in the large delta phi limit looks like this. So basically the same factor, but with C exchange with MB, or sorry, ZB. So to get these blobs where things diverge, we need to look at this expression here, the limit of A times G. And you see that you either get 0 or infinity, depending on when this factor in square brackets is below or above 1. And okay, this is simple to see because we are exponentiating this to something that goes to infinity. So if it's smaller than 1, you get 0, and if it's larger than 1, you get infinity. So this line here for the blob is defined by this equation. So this is how we get the blobs here. And now about the finite part of the Polyakov block. For this, we will use the relation between master functionals and Polyakov blocks. So this master functional will have a piece that contains this factor here, where we're evaluating, integrating the conformal block with this kernel defined here again. And as I said, this conformal block has a saddle point at some ZB. So basically this integral just gives the kernel evaluated at ZB with some A-free factor. But we know from the bound I saw above that this factor here is finite. So we get some finite piece with the Cauchy type kernel here. And this is really the flat space limit of the Polyakov block, which gives the bound state pole. So this is how we recover this part of the S matrix once you match all the kinematic factors. Okay, so that's how it works for a single block. But you can do it also for the sum of different blocks. So you see that if you start with some correlator and expand it in Polyakov blocks, then you separate the identity contribution, the states below threshold, and the states above it. And this flat space limit will give you 1 for the identity, some integral, because this sum over delta becomes an integral over some S prime that runs from some S0 coming from this gap, so the next operator after identity, all the way to threshold, which is this 2 delta phi. And then a similar thing for above threshold. So in the example for the single Polyakov block becoming a bound state pole, you would have this rho tilde become basically a delta function. So this dispersion relation is very important. Why? Because actually we are writing this dispersion relation in terms of CFT data. We could have started assuming some analytic properties of S and just write directly a dispersion relation. But what we did was different. We started from some CFT correlator, did some flat space limits, and then write a dispersion relation for the S matrix just in terms of the CFT data. So these densities here are related to the OP coefficients, as I say here. So there's this map between S prime and delta. So in this way, we're, as I said, showing the analytic properties in terms of CFT data. We have crossing symmetry by construction because we're expanding in Polyakov blocks. And yeah, I don't have time to explain it, but these are also unitary S matrices. So they satisfy this property here for S physical above 4m squared. And this comes from basically saying that the OP coefficients are on average the same as the generalized free fields, the OP for the generalized free fields. So a hint of how this unitarity comes about is that we start with this bound on the correlator itself I mentioned before, and from there we can get this average condition, which is actually this one here, which says that for states above threshold, this ratio of A over A free with some Gaussian measure gives 1. So it's in this sense that they are the same on average. But so are we done? And not really, because we were assuming some gap here such that everything is finite when we do these flat space limits, in particular that these rows are finite. And so this is the last point I have time. Okay. This is the last point I want to talk about. However, we don't only have bound state poles or two particle thresholds. There are also the so-called anomalous thresholds, which are singularities in the S matrix, which you cannot directly interpret as some physical state flowing in the middle. And you can get these specific singularities by looking at Landau diagrams. So these are diagrams like Feynman diagrams where you put all legs on shell, so also the internal ones. And these diagrams give rise to these extra singularities, which in two space-time dimensions are just poles. They are usually branch points in higher dimensions. But an important thing is that you cannot draw these Landau diagrams or put everything on shell unless there's a specific ratio between the internal particle mass and the external one. So you can only have these singularities when m2 squared is below a half of m squared. And what we're claiming here is that the anomalous thresholds are related to some unboundedness of the OP. So let's go back a little and see how we could get some unbounded OP. So if you remember, we were using this Sine-Gordon bound for the OP coefficients below threshold. But there is this point here in the middle where it's actually unbounded. So whenever we have a state such that its dimension is square root 2 delta phi, we don't have a bound for its OP coefficient. So we run into problems there. Another slightly more complicated scenario is that we have some crossing symmetric pairs of states that satisfy this property. So in terms of these masses, we have that some state with mass m squared and some other state with mass such that it's 4m squared minus, where this m squared is the external leg, minus this. So, and why do we run into issues here? And it is basically because these extremal functionals in the flat space limit are anti-symmetric. So if you have some state here, then its crossing symmetric counterpart here will have an opposite sign. And if you remember, in order to get bounds, we need to have a definite sign for the functional. Otherwise, you have something negative plus something positive. You can make them infinity if you want. So this is how we can get something unbounded. And to go back to this range here where you can have extra singularities, let's see how it would work with this unboundedness. So if we have m2 squared below 1/2, then the two particle threshold for this particle will start at 2m2 all squared. And this touches this difficult point 2, where we don't have a bound. So indeed, whenever the internal mass is in this range, we don't have a bound for its OP coefficient. So it makes sense that the flat space limit is not entirely well defined. Something goes wrong and you can get some extra singularities. So this is the one idea to see how this claim could be true. Well, it's true. Another idea is that you can actually see explicitly that you can add solutions to crossing to your original correlator, such that this new term has a 0 flat space limit. So a flat space limit of both would be the same as the original one. But these new solutions to crossing can have, well, positive and arbitrarily large OP coefficients. So that's another way in which you can get something unbounded. These crossing solutions can look like this with some parameter alpha. But crucially, you can only do this for a gap below certain point. So to see this in a specific example, something we did in the paper, which I won't go into any detail because I don't have time, is that we took the box diagram here in flat space and also the Witten box diagram. So free scalar fields in ADS with these couplings such that you have this diagram. Now you can write some CFT density, which will be related to the OP coefficients. These OP coefficients, you know, from the OP decomposition of Witten diagrams. And in the flat space limit, they should match with the discontinuity of this Feynman diagram. So in a plot, in black, you have the discontinuity of the box diagram here. And then these rows, you compute numerically for some finite but large delta phi. And at this point, and you see that in this range where M2 squared is larger than 1/2, so the safe region, they match perfectly. If you go into the anomalous region where M2 squared is below 1/2, then you run into some issues. So indeed, something goes wrong with the flat space. So that in principle, it should match this flat space computation, but it doesn't. However, the part where it doesn't match, you can actually trace it to one of these spurious solutions to crossing. So if you construct this correlator and take the OP coefficients in some finite but large delta phi and plot it, you see that they give basically the same as a mismatch with a flat space density. So this is these are just some broad ideas of how we could get anomalous thresholds to work. So we know why they don't work, but we still need to think more about this pure solution to see how to get this actual singularity. So this would give some double point the amplitude. How do we get it? So there's still some work to be done, but I will end with some remarks. So a one-line summary of what I tried to tell you is that we can get analytic, crossing, and unitary S-matrices in 2D from 1D CFT correlators in a specific limit. And we see that indeed we recover everything we expect for the S-matrix. Now for the future, as I said before, we would like to clarify how to get the actual singularities for the anomalous thresholds. There are many generalizations we can do, global symmetries, higher point functions, higher dimensions. Yeah, there's plenty of space there. One other interesting question would be to understand how do we get intervalous matrices from the CFT point of view? So we know in the QFT, they should satisfy some Yang-Baxter equation, which I explained on the last year. But we don't know what it should, what this constraint means in terms of purely CFT. So it would be nice to see which CFTs give rise to intervalous matrices. And I think I'm done with that. Yes. Thank you.
Thank you very much, Dr. Lucia, for this interesting talk. We have time for questions. Please go ahead. I think so. Oh my God. So let's see. Brian. I think Brian raised his hand. Okay. Matthew.
I think they were clapping.
Oh, yeah.
Sorry, that was just clapping.
Oh, okay. I got confused. Sorry. Well,
I got more like a general question, if I might.
Yeah, I don't see this. Yes, okay.
Right. So hi, Lucia. Nice to meet you virtually.
Nice to meet you.
Right. So I guess the reason why you guys choose to do two-dimensional conformal field, sorry, one-dimensional conformal field theory and two-dimensional quantum field theories is because you guys are just starting to develop this technology and want to,
it's the simplest scenario, yes.
Right. So I was wondering if you guys have thought about, in the two-dimensional case in conformal field theories, we have this huge family of integrable theories, minimal models, rational theories. So what do you guys expect to happen in you have all this structure in these two-dimensional conformal field theories. Do you have an intuition what's going to happen in the three-dimensional conformal field theory, quantum field theory?
That's a great question, and no, I don't have an answer for it, but it's definitely something.
So you guys don't have an idea how integrability map from one side to the other, or that's still
No, so we know about interval S matrices, and okay, something I didn't emphasize, but these S matrices that we get are usually, sorry, let me rephrase it. So interval S matrices satisfy, among other things, saturation of unitarity, because there's only 2 to 2 scattering. So the the S-matrices that you obtain from CFTs that saturate unitarity in this simple scenario without global symmetry are indeed, you can see them as just some CDD poles or CDD zeros, so some known interval solutions. However, this flat space limit erases a lot of information, so you can actually get the same result by adding things that have zero flat space, as I was saying for the anomalous dimension, anomalous threshold, sorry. You can also multiply by things. So this flat space limit erases information. So yeah, there should be some big family of CFTs that map to the same S matrix. But yeah, we don't have a clear understanding of what is this big family mapping to.
I think you have got a good point. So when you take the flat space and you take this dimension to be very large, do you need that the spectrum of the CFT contain operators with these very large dimensions, right? Like, is that what we when you
usually we need to have the identity, so dimension 0, but you always have the what is called the double traces of phi. So phi is an external field, and you can always construct operators which have dimension 2 delta phi plus 2n, as for the generalized free fields. Yeah. So these are always present. I don't know if these are the large delta.
Yeah, I see.
Operators.
Yeah. I was thinking in the primary operators dimensions, but then these dimensions that you are taking to infinity could be, could be composite operators or
yeah.
Gotcha.